Okay, so welcome to our 5th KCS talk today, all right? The speaker for today is Dr. Xiao, and he's a faculty member, the junior faculty member of our department. And the title of his talk is Blockchain, DApps, and the Trustworthy Computing. Okay? And Dr. Xiao will first explore the general principles of harmonizing blockchain with trustworthy computing, and then cover 2 recent research results. Okay, he will tell you what those results are, and lastly, he will touch on the other direction. Can we leverage blockchain and distributed ledgers in general to strengthen security and reliability of existing trusted computing systems? Okay? And as that Mr. Kevin has expressed, if you have a question for the speaker, please speak loud, okay, so that the recording system can pick up your question. Of course, if it's possible, can you also repeat the question? Yeah. Thank you very much. Thank you very much.
That wasn't clear.
Yeah, well, let's welcome our speaker.
Thank you, Dr. Chung, for the introduction. So my name is Xiao. I am here for almost 1 year. So I'm still excited just as a freshman. So basically today, sorry, excuse me. So I'll introduce my thought, which should be very, very coarse at this time, about how to combine blockchain, DApps or DApps with trustworthy computing. So trustworthy computing and blockchain, they seem to like 2 very different fields, right? Because blockchain is known as cryptocurrencies, Bitcoin, all the ups and downs in the prices. So how does that relate to, computing in the time being? So let me just briefly give you some introduction on our field. So the technology of blockchain has its origin in Bitcoin. Everyone knows that. So the creator of Bitcoin, the pseudonym is, so the name is, I suppose he or she is Satoshi Nakamoto. So nobody knows who that guy is or was. So basically, he wrote a white paper in 2008, and that paper is the Bitcoin white paper. It's like a Bible in this field. So the year after that, in 2009, Bitcoin began to mine its first block, and that becomes today's Bitcoin. So as you have to know that the price of Bitcoin up and down, that's basically running from the very beginning of the white paper. So as you may not know, we had some kind of a legacy digital cash system before Bitcoin. So most likely, those kind of a cash system is no longer used in our society. So basically, before I introduce what are those requirements, so a digital cash is different from a digital currency. A digital cash has to be offline, anonymous, just like dollar bills, paper money. So you can just transact with your paper money instead of, say, relying on the central online banking system or its processor to deal with the transactions. So it has to flow like cash. It has to address the security problems of counterfeits and double spending. So none of the previous legacy systems dealt with them in a very satisfying manner. So not until Bitcoin. So I give you some names which have been very well known in the field all the way from 1983 to 2005, and in some cases in big money and the big gold, they are already very similar to Bitcoin. So in some of the decentralized, how to process different ledgers, how to put transactions in the ledgers, so they are already very similar, but they are not Bitcoin. So what Bitcoin does is really interesting. So Bitcoin enables a decentralized and offline transaction processing. So basically, if you join this network, you can send a transaction, say sending money from my account to your account, and you don't need any central authority to deal with the processing burden. So you can just everybody in this network, all the peers, process the transaction for you. And at the same time, you are not revealing your true ID. You are using an anonymous or pseudonym. It's like a string of, it's like a 20-byte string as your address. So anybody in this world, if you have some money in your under account, you can send this transaction and under your pseudonym. And at the same time, which is most importantly, how to deal with the double spending, how to present the Bitcoin just like cash. So the transaction is processed through consensus, through cryptography. So by the signing and verification of signatures, you are basically delegate which used to be done by the central authority to the decentralized community to the transaction processing and verification. And everybody then put the transaction in that. And then which comes to, I think what is more important is, so from the second generation of cryptocurrency, they are no longer a currency. They are also a computing system. So what does that mean? So basically, in the case of Bitcoin, whenever you send a transaction, you can attach some kind of condition in the script, in the transaction script. And you can say, if some hash condition happens, I can release my transaction at a later time. And this simple hash time lock is like a preamble or a prototype of later known as smart contract. So the second generation of blockchain, the core idea component is called smart contract. So basically, smart contract is kind of a Turing complete object. It's a language for you to program any kind of functions, such as an if, a while loop, and even any kind of computing tasks. So smart contract, if you use them well, it can give you a very powerful tool to enable any kind of a real-world contract. You don't have to rely on any intermediary or escrow agents to deal with the money transfer or some kind of any kind of a function in the on-chain field. So basically, I define smart contract as a stateful program running on the blockchain, and it executes encoded functions per invocation. So anybody can publish a contract, and then anybody can just invoke the contract functions to execute your designed functions, and there's no need for trusted intermediary. So this basically renders blockchain as a computing platform, because you can just encode any kind of function like an add or even machine learning algorithms if a contract is powerful enough in the script fields to do your personalized computing tasks. So without giving you more details, I'll discuss later. The third generation of blockchain is known as to enable the Web3 applications or DApps. So without giving you details at this time, DApps covers a wide spectrum of applications from DeFi, decentralized application, social media or decentralized social media, gaming, and the NFT markets. So anybody here has heard of NFT before? All right, I know of you. And ID management and online voting. So all of those applications, they are used just as a normal application, but they use blockchain smart contract as a backend to store and process multi-person data. All right. So in today's talk, I want to briefly first go through what are basic concepts of blockchain, smart contracts, and DApps, and then go into what I want to focus on in my kind of a near future for my research, trustworthy in blockchain or for blockchain. You can think of trustworthy computing and blockchain as two subjects. You can use blockchain for trustworthy computing, and the other way around, use existing trustworthy computing techniques for improving the security of blockchain. And then below in that path, I want to introduce two of my recent work. The first one is PrivacyGuard. It is actually designed for different purposes, but somehow aligned with my goal of trustworthy computing in blockchain. The second one is called DecenTruth, which is a very recent work. It actually uses kind of data mining techniques to help blockchain to improve the security from a data perspective. All right, let's begin. So the blockchain system in a nutshell is a distributed ledger system. It has a network of peer-to-peer nodes. Each node receives and verifies and disseminates transactions. So basically, if you are a client to a node, and your node can accept your transaction and disseminate to everybody else in the network, and then they will verify and finalize your transaction in the block. And the new block will be added to the ledger, which is known as blockchain. So each node keeps a replica of the transaction ledger, and every node finalizes a unified, correct, and immutable ledger, which is done by consensus. Again, not by central authority, but by consensus process. So, but from that point of view, it's so coarse, we don't see any details from that kind of the term definition distributed ledger, but we want to dissect the system into more details. So as a computer networks person, I want to view the system as from a layered point of view. So the system of blockchain consists of 4 different layers. The first one, from bottom-up approach, is a peer-to-peer network. So all the nodes or peers, they are connecting to each other, say, peer-to-peer connections by doing first peer discovery, and then talk to each other, say, can I be friends to you, and you can be friend to me, so something like that. And then the blockchain ledger is basically a chain of blocks. Each block contains some transactions in that period, which has been successfully verified and put into that ledger. So, and then most important, in my opinion, is called the consensus layer. So consensus basically helps every node to finalize a unified transaction ledger, so which again have to finalize the transaction individually in the first place. So by doing the transaction protocol, so everybody should have the same ledger at the end, or at least periodically. And then, based upon the 3 layers below, we have then, which becomes exciting, is the apps, the applications. So in the application layer, we can have transactions, right? Send money from you to your friend, and accounts, so and a smart contract and a Dept. So based upon the scripting feature of transactions, we're building the smart contract. And then based upon smart contract, we are building Dept. So Dept basically use smart contract as its backend. So I'll give you more details later. So basically, smart contract, can regard them as a stateful on-chain programs. It's like itself is individual state machine, has variables, has functions. But at the same time, all the smart contracts put together in the entire blockchain is called a global state machine. Again, another state machine. So as you may know, for a state machine to work, there should be no randomness in the functions. So when you send a transaction to invoke a contract, you are sending an input to certain functions, and that function will give you an output, according to that input. So by doing this, everybody does the same, will have the same outputs, and then the output will be finalized to the new state. So this may be very similar to some kind of older concepts called Byzantine fault-tolerant state machine replication. So state machine replication is a classic research on distributed computing. So a kind of a consortium of nodes receive a single stream of transactions and make the same decision and output the same decisions to the client. So basically, smart contracts does the same thing. So that's why, as I just mentioned, you cannot tolerate any randomness in this computation, because if we use random source in the functions, so everybody will have different results, which is a counter idea of state machine, of a fault-tolerant state machine. So these are just the basic high-level concepts of smart contract. So to give you a rough example, I use Ethereum. So like I said, Ethereum is a second-generation blockchain. It uses Solidity as a programming language, Turing complete. So basically, based upon this blockchain transaction scripting capability, it enables something called the Ethereum virtual machine. So this virtual machine, just like a OS, operating system, but it's decentralized, it's not centralized. Yeah, you can encode smart contracts on top of it, and then just like the stateful programs. So here gives you one example of one smart contract. It's called a vending machine. So the owner or the creator of the smart contracts can deposit some kind of values and coin. So the purchaser or client can just invoke this purchase function by using some kind of Ethereum cryptocurrency to buy online messages, to buy online tokens. So this is just a very easy example of how smart contract works. But of course, it can enable a much more complex exam. Say, what if the purchase encodes some kind of a very complex computing task, and at the end, the purchase function can give you the computing results as a byproduct of your vending machine. So this is just one example of Ethereum smart contracts. But what we want to make a distinction here is Web3 applications is different from Web2 applications. So Web2 what refers to the current cloud-based applications. You are accessing a service provided by some guy in the cloud, and the database will give you a response just like a client server. But in Web3 Dept, you are not relying on that in a centralized database. You are relying the backend processing on the Ethereum smart contracts. So you want to transfer money from you to your friends. Normally, if you are using the bank's backend processing, so the single bank, Chase or Bank of America, they can do that in the centralized manner, right? But in the Web3 Dept, you are relying on the whole virtual machine, a decentralized system, to fulfill this transfer of value. So the idea is the Web 2.0 is centralized, it can be closed, it can be non-transparent, but for Web 3 Dept, the backend can be transparent, decentralized, and everybody should be aware of what happens on this backend machine. So in many cases, although this idea was very decentralized, but still, when the industry evolves, there emerged some kind of a blockchain API, because not everybody wants to write its own blockchain node, right? Because that's very costly and a huge amount of memory costs. So there emerged some commercial entities. They are providing access points service, so you can access the backend going through my blockchain node API. So again, by doing this, the DApp designer or DApp provider don't have to worry about running a blockchain instance, but focusing on the programming servicing part. So this is the core idea of Dept. So as you can see, the really tricky part is the backend. So everything beyond the user space is almost the same. You can use the same user device, same applications, and same user mobile phone or browser to see the application status. All right. So now we have introduced the very basic high-level idea of blockchain, Dept, and smart contracts. So it is by no means a comprehensive introduction on those kind of technology, because I have given so many details on how the transactions are finalized, or how the smart contracts are processed are compiled in the, say, from user space into the bytecodes. But now I want to focus on my research. The thing is, the topic is called trustworthy computing for blockchain. So before talking about our main goals, so I want to raise you some concerns from me on smart contract and Dept. The first one is privacy concern. So as you probably remember a moment ago, I said everything written on the backend smart contract is transparent. It's known to anybody in the world. So what if you are a security aware person, you don't want to expose your amount balance to everybody in the world? So in this case, privacy becomes a huge problem. You don't want to expose all the contract state variables to the public. The second one is efficiency concern. So again, because you are using a decentralized operating system, so virtually every transaction has to be executed by everybody in the network, so it has to be multiplied by n. Again, it's a huge amount of cost. So that's why the blockchain transaction itself, and let alone the transaction invocation function in the smart contract, could be very, very expensive. So when I was doing my experiments, like almost 3 years ago, one transaction cost me about $1 or $2. So at that time, the Ether price, I think it was only $200 a piece, but now the Ether price is more than 2,000. So as you can see, the price is really can be prohibitive if you want to realize a more complex programs with smart contract. So again, somebody wants to, so there have been a bunch of research using pure cryptographic solutions like multi-party computation, homomorphic encryption, or to realize the privacy preserving computing. But those kind of ideas have to be realized as a function in smart contracts. Again, homomorphic encryption or multi-party computation is already very expensive without, so in the centralized domain, so you can even more costly multiply by n if you are doing that in the smart contract. So it's not very worth our efforts. So the question is, can we build a privacy-preserving and efficient smart contracts? That's one of my research direction. So the second one is some kind of external concern for the smart contracts. So very likely your smart contracts, if you are designing a DeFi application or say a prediction markets, your application depends on some external data, the weather of Lexington and the price of today's US dollar to Chinese yuan. So you are relying on that external data for executing your own multi-party logic, and that data is out of your control from your consensus protocol. Your consensus protocol can only verify what happened in the blockchain, but it cannot verify anything beyond the blockchain. So this is known as external data concern. So the current blockchain system relies on something called blockchain oracles to do the stuff. So oracle basically acts as a transportation agency to gather external data from outside sources into the blockchain smart contract. And the smart contract can then build their own logic based upon those external information or trigger events. So, and the fourth KPI of smart contract is, so even smart contracts is designed to be secure from the beginning, it cannot prevent, and so the minor mistakes, by minor mistakes I mean it can be very big in consequences, because so if you know the sheer scale of the money value of the smart contracts, one contract manages millions of dollars. So but you only have like 200 lines of code. So basically, on average, one line of code can manage like tens of thousands of dollars. So it's so costly. You have to be so secure. You have to bear in mind that every design mistake you make will have severe consequences. So at the end, we have seen the 4 different design areas for smart contracts. But so and then this leads to our concept called trustworthy computing in blockchain. So before that, my question is, can we eliminate or at least minimize the external risks to smart contracts and DApps? So here we can see the 2 research directions really is the main focus, or has been the main focus of my research in the last 2 years. So let's talk trustworthy computing in blockchain. So before I thinking about the trustworthy computing in blockchain, so the concept of trustworthy computing has already appeared in various fields. So the earliest version of trustworthy computing was proposed by Microsoft, by Bill Gates himself. So it covers the confidentiality of clients' data and reliability of the computation and the availability of the computation. So, but we're not dealing with that definition, because that is just a basic concept. In our case, we want to say improve the blockchain smart contracts, or at least make something relevant between smart contract and some trust in our system. So the first thing we can do from our first research direction, how do you privatize, or how do you implement confidential application with smart contract? Right? You don't want to expose every data you have in the smart contract. Second thing is integrity. So what if you don't trust the smart contracts for executing some applications, because you suspect the smart contract is using illegal random source from the beginning? So somehow you want to have a better control on the smart contract. So another issue. The third one is availability, liveness of execution. So very likely, if you are using Ethereum, you want to pay a higher fee to get the transactions faster processed. So if you're not so rich, you still want to process the transaction very fast, this becomes an availability issue, right? You your transaction, your contract invocation to be so slow, maybe 2 or 3 of delays. The first one is reliability of external data. Like I just mentioned in the last few slides, the quality of external data will significantly affect the results or outcomes of your business logic. So here the four concepts is my own definition of trustworthy computing in blockchain. But by the way, trustworthy, the term can be very controversial because it's so subjective, because trust can always be subjective. So to realize trustworthy computing, I want to use some technique from the trusted computing domain. So again, I want to differentiate trusted computing from trustworthy computing because they are focusing on different things. So trusted computing basically focuses on how to use trusted hardware to shift the trust to some kind of a physical device. The idea is, although you cannot trust any single individual computer, but at least you can trust some hardware root of trust, say a single chip, because it cannot be modified. You can believe that everything written inside the chip or the combination memory should not be tampered with. So this idea is called the Trusted Execution Environment, or TEE. So Intel, AMD, or all the main chip vendors, they are all incorporating TEE in their own chipset. So basically, it provides a secure area of main processor, an isolated environment guaranteeing the confidentiality and integrity of data and code. So there are some just 4 basic vendors of this kind of technology: ARM, Intel, AMD, and RISC-V. So these are kind of very heavily used in the industry already. So because I don't want to cover the details of each product, I want to give you a high-level idea on what TEE can provide to our case. So because it's a secure area inside a chip, so it provides 3 core functionalities. The first one is data confidentiality. Everything you put into this secure memory should be secure. Nobody should be tampered with and know what it looks like. The second one is data integrity. So nobody should be tampering with that data. And then the code integrity, which is so important that you can write a piece of program inside this protected memory or the chip's cache, and then you can just ensure that nobody can change this code, and you can even prove to your outsiders that my code has always been like this for the past few days. So the idea is called attestation. By doing attestation, you are providing a proof that yes, I'm really executing your program, which you gave me several days ago. So by giving you a proof, which should be signed by a key inside this secure enclave or secure memory. So all these measurements is a proof for that my code or program is secure is just as what you give me, right? So this idea is very powerful that you don't have to worry about. You don't have to worry about somebody else will change your code inside the secure area. But at least you should trust the chip itself is not tampered with, and the signing key inside the secure enclave should not be tampered with. So again, like I said, trustworthy is controversial. You are not doing a zero trust scheme. You are shifting trust. You are shifting the trust on individual hosts to the trust on a single chip. It's called a hardware root of trust. So it's different from a TPM, it's like your SIM card, because those kind of things does not support code integrity, programmable code in your scheme. You can only store very basic keys or information, like your subscriber information, but a TEE, you can build them as extension to TPM, powerful opportunities, powerful functions to realize programming schemes inside the secure enclave. All right, so I'll just skip the details of a secure and enclave. But what you have to maybe need to know here is both Intel and ARM, they are realizing there are all different versions of TEE and they have different implementations. The core idea is the trusted applications or enclave is always in the trusted area, and your operating system and everything else which is not within your enclave should be untrusted. So say this is your host machine, and your applications can be put into the secure memory. Okay, so now we move to some of my recent works on using these two technology together, blockchain and trusted execution environment. So actually, the first application is called PrivacyGuard, and the second one is called DecenTruth. So actually, the second one does not actually use T for the time being. It actually use another concept called truth discovery to help you discover external data, the ground truth of external data. But the first work, PrivacyGuard, it was designed actually for a different purpose that happens to align with this kind of path, how to combine blockchain and trustworthy computation to realize a bigger goal. So when we proposed PrivacyGuard, our purpose was different. We want to solve the privacy problem of data misuse. So at that time, so in the year 2018, so we have something very infamous example called Cambridge Analytica, the data scan. So more than 85 million Facebook users' profiles have been harvested, used for illicit purposes, potentially for social engineering against voters, right? So this it's a very severe event in my point of view. So somehow at that time I was thinking, can we use blockchain to solve this problem? So the thing is, whenever you have some company use your data, so in the current regime, you are signing a user agreement. Once you give your data to outsiders, you have no more control. But what if we have blockchain? So what if every usage record, every usage steps is recorded in blockchain, and this will be a kind of a proof that the usage actually happens, and you can use that as some kind of a evidence to show that people are using your data illicitly or for whatever purpose. So actually, from the legal perspective, the European Union's GDPR regulation already regulates we have to observe the rights to restrict processing, and the right to object. So which means that the users, the data owners, can always control how outsiders can use our data, or how my data should be viewed or not be viewed by external parties. So, but in this application, we seek a technical solution instead of just a legal from hindsight perspective. So our solution, PrivacyGuard, will make use of blockchain and trusted execution environment. So you can view PrivacyGuard as a Dept, but at that time when we proposed PrivacyGuard, the concept of Dept was not there. So if our PrivacyGuard Dept basically protects the confidentiality of private data. So basically, a user of our Dept can regulate who can use my data for which purpose at what condition or price. So if you want to use it, only ask, say, 23andMe to use your DNA records for genetic disease search, you're not expecting some other companies like your insurance company to check to increase your premiums. So the data usage really considers about the confidentiality of your private data. So no matter who uses it, you have to say they did not view my plain text data. So I'm only get the results without seeing my data in the first place. The second thing is you have to control the access and the usage of your data. So only those guys can, with those payments, can access my data and use that for that programming or computing task. And then what's more interesting at that time is I want to realize the data markets, because a DApp or Dept is a commercial application. I want to allow people to profit from selling their data or selling the usage of data at least. So that in the data economy, so the data owner can just, or the customer to our application can publish a data usage rule on the contracts, and then so anybody uses my data or uses that for computation should be recorded and pay me a fee. And the operation should be publicly written on the smart contract. So doing this, if your computation is calculating the average of your blood rates, and the operation should be the average function of your periodic blood heart heart rates of your medical records. So this is a very basic idea using smart contracts to realize all this. So some of these targets. But so here comes a very straightforward solution with smart contract. The first one is you have individual data owners publish a smart contract on the blockchain. And then the data consumer just invoke this smart contract and get the computation results, right? And everything will be recorded perfectly. But is that good enough? So we have recorded every transaction. We have solved the data misusage recording problem. But what is missing is the confidentiality of your data, because whenever you publish your data and the contract on the blockchain, you are risking, you are considering that everybody should have access to it, which is not desired in our case. So we have to somehow use some kind of option execution mechanism to execute that program off-chain in the TEE instead of using the plain text on-chain. So the idea is to move the data operation off-chain so the confidentiality can be protected, plain text should never expose, scalability is want to avoid costly on-chain computation. So we're combining blockchain and TEE. So basically, the brief idea is whenever you encode a smart contract, we have to replicate that in off-chain TEE. And this we're doing the same computation which was supposed to be done in the on-chain space. So in our smart contract system, basically, the off-chain space consists of IData agents, which gathers and encrypts users' data, and some events when data consumer invokes the smart contract. So everybody in this in the off-chain space will know that the data consumer has started a data transaction, and our DApps should start to work, start to function to compute the program tasks. So at this time, the encrypted data should be gathered from the IData agents and will be decrypted inside the secure enclave, the TEE. So at this time, the results will be executed, will be obtained in the TEE, and will be somehow delivered to the corresponding consumer, which is a data consumer. So this is a brief idea of our privacy DApp. So basically enables a person or client to safely monetize or cash out on his or her, say, private data. But there's one thing remains: how to deal with result commitment. How do you safely commit results to data consumer and deliver the transaction fee, the payment to this data owner? So this is kind of called a fair exchange problem. We want to commit the results at the same time commit the payments. So without further details, we designed something called a result commitment protocol to guarantee the atomic execution of two things. First one is to deliver the money to data owner, and the second thing is to deliver results to the data consumer. So by doing that, we have shown a proof. So if something bad happens, if IData agents collude with hosting platform, this is called a spammer DO, who wants to get the payments without implementing the computation. This can be prevented. So the second attack scenario is, what if the data consumer wants to collude with the host, say to get a free rider experience? I can get results without paying any fee. So this is also subdued because of our result commitment protocol. So we can refer to our paper for more details, but this is a really exciting that at the end of the day, the smart contract has a final say on when to publish the results, and at the same time publish to divert the payments from the deposits to the data consumer simultaneously. So it's called a fair exchange. So if it is done correctly, we can enable a data market for private data. So this is our design of PrivacyGuard DecenTruth. So we implement our design, and the code is available in GitHub. So this basically shows the published the data contract here. So by the way, data broker is another type of our IData contract, which basically means it can behave on behalf of collection of data owners. So I can broker your private data on-chain, and everybody have interest, clients have interest, they can just invoke this contract and ask for results, and I will deliver their payments to your accounts. So this is basically the brief idea. So I will skip the evaluation results. So the next thing we want to focus on is to address the second issue of external data rate. Like I said, the PrivacyGuard addresses a computing problem, but so from my point of view, what if my PrivacyGuard contract has to use external data, right? So say if you are using some computing tasks which relies on the weather information, depends on the financial information from the exchange data from the say public exchanges. So what do you do? So even if everything is perfect implemented from blockchain side, so what if you get bad data from the outsider? So this is a problem called the oracle problem. So because you are relying on some kind of a centralized oracle to transfer data from outsider to your blockchain environment. So the existing solutions such as Chainlink, Lightning Protocol, they are commercial solutions. They are just a centralized entity or a collection of entities. They are getting data, they're gathering data from external sources and then converge them or taking the average or median. So for all the available different versions of data and then converge them into a single version of data and put it on the blockchain smart contract. So but at the same time, I ask myself, so is that trustworthy? So because blockchain itself is pretty much decentralized platform, but you are relying on some kind of trust guys to doing the data transfer on behalf of you. You have no more control on the data from outsiders. So from my point of view, if I'm running a $1 million business with smart contracts, I will have to at least have some control over how the data is screened, how the data is processed or produced in the first hand. So that's why, so in the current commercial schemes, they are relying on something called the decentralized oracle network to transport the data from external sources to the blockchain network. So for example, we have 3 different data queries. The first one is the stock prices of Nasdaq 100, or the temperature of Lexington, or the Bitcoin to either rate. These are all data subjects. You want to ask, so the blockchain customer contracts has to ask the oracles to gather data from distributed sources from the real world. So again, you have to trust those oracle nodes to doing their part correctly. So this is a concern to me, and it's a concern to many because I believe in October last year there has been already a big hack on the cryptocurrency oracle, which has resulted in a huge amount of monetary loss because of one or two the oracle nodes has been compromised, which gave the application wrong data from the outside world. So in this direction, I want to solve the data reliability problem. So because the authenticity and the integrity of data feeds, which consider how to transport the outsider data into the on-chain part, can be done by TEE, by trust exchange environment, and the on-chain cost efficiency problem is another issue. So from my understanding, this segment has been already addressed, but the first one, on-chain cost. So how do you say screen your data in the on-chain space? What if you want to use a complex algorithm to process your data in the on-chain space, which can be very costly? So it is partially addressed because in Chainlink and other commercial oracles, they are rely on taking the medium of all the available data versions. So which, in my opinion, is not good enough because taking the medium is by no means the perfect way to deal with that data. So the third problem, I believe, is more severe, is most important, is nobody just addresses the source reliability problem. What if legitimate sources provide bad data? So basically, if you are relying on that source, that oracle for that data entry, so you are doomed to your DApp application. So if that happens to be bad data sources. So in this work, we borrow some idea from a data mining research called truth discovery. So truth discovery is basically a distributed, kind of a distributed data gathering process or the crowdsourcing algorithm. What if you have multiple sources for a single data entry? So how do you reliably gather the trustworthy version from multiple data entries, right? So the idea is you want to evaluate the trust score for each source, and then based on the trust score iteratively, you update the weighted average of your data entry. So for subject 1, if you receive this bunch of data from all the sources, you are doing the average based on the initial weights, and then you go back and update the weights for the trustworthy score of the sources, and again update your new estimates of the ground truth. After so many runs back and forth, you are converging to a finalized version of estimated truth from the multi-source data. So this process is known as truth discovery. And we want to use truth discovery for our purpose to discover or to at least estimate the ground truth of external data for blockchain oracles. So we borrow the idea of two lines of TD research. The first one is streaming data. We want to somehow format our algorithm in the streaming to accommodate streaming data in the time being not on a monolithic data set. The second part to deal with is because we do not have a centralized aggregator in our blockchain system. How does different oracle nodes so you react to each other without relying on a central authority to aggregate data, but still have to trust each other? I mean, the only thing that trust is the majority is honest. You cannot trust each other individually. So that's why we come up with our solution. It's called DecenTruth. So DecenTruth is basically is a new blockchain oracle system. It's a decentralized oracle network. So every oracle node should operate a DecenTruth software. So the software basically is a combination of truth discovery and consensus protocol. So again, consensus protocol is from blockchain, and the truth discovery is from the truth discovery. It is from our, say, the TD research. So basically, what we have done is we have two components, the TD and the ACS. So ACS is a type of consensus protocol that, so whenever each node, you have proposed local truth estimate on your local sources, and then you're doing this kind of asynchronous consensus so that everybody agree on the same value on a single data subject. So at the end, when you have a common set of proposals, everybody should do the same truth discovery algorithm, and then come up with the same finalized truth estimates on external data. So as you can see that, the end result X hat will be delivered to the smart contracts, and the weights will be feedback to the next round of truth discovery and consensus process. So this kind of iterative process helps everybody in this network, DecenTruth nodes, to estimate each other and each other's sources in a very consistent manner. And at the same time, for every epoch, I provide a data feed to smart contract, and then so we can guarantee that all the data is produced in a trustworthy manner, not from a single point of failure, not single point of data sources. So I'll skip the details of how DecenTruth was designed, because although it looks very, very simple, but the consensus protocol design is not trivial, because we're considering a very severe asynchronous communication process. There's no timing guarantee whatsoever between different nodes. So what you can only rely on is the message delivery itself, not on any timer. This gives you maximum compatibility of all the existing offline, off-chain oracle nodes. So we evaluated our scheme on a simulation platform. So basically, the figure here shows the routed links, where error rate of our say the discovered estimated truth compared with existing schemes. So the color curves are our scheme, and the black lines are the existing medium schemes of chaining. So obviously, because we are using truth discovery instead of medium, our scheme has a better performance. So The idea is very simple. We are realizing the truth discovery, which was supposed to be a centralized matter, but in a decentralized scheme. So the accuracy improvement should be obvious, but so again, this demonstrates the long-term accuracy of our scheme compared to chaining. And what I want to mention is, so because we are doing the totally decentralized consensus protocol-based truth discovery, our scheme still suffers from a huge amount of overhead. But because of the consensus scheme is so costly, so even for one estimation round, so it risks using more than 1 minute of computation time, right? So this is our current direction. We want to use a more efficient consensus protocol to help different blockchain oracles to reach consensus on this external data. So only after doing that, we can fully commercialize our product and say you can use our almost real-time data. Otherwise, 1 minute is too low for adoption. So this paper is accepted in InfoComm this year, will be presented in May in New York. So what I want to say from this work is, this still remains so many different loopholes, so many vacancies to build it, such as the efficiency problem and for the oracle design. So I want to work on this domain, and so if you have any kind of idea, you can let me know. So how to improve the efficiency of oracles and still guarantee the trustworthiness of TD process. All right, so for the time being, we have finished 2 different directions of combining blockchain smart contracts with trustworthy computing. But what I have in mind is we can still improve these two schemes together. So either to improve the current performance or to enable more different new applications. The first one I can think of is, so because as you can see the figure on the left is the current oracle scheme, which is used by both Chainlink and our DecenTruth scheme, right? You build an oracle and gather data from the external world and put it on the blockchain. But what if your different DApps want to use each other's data, right? So in many cases, DApp1 shares some similarities with DApp2, but doesn't have that data source. So this is commonly already seen in our current blockchain environment. So what is most likely in the DApp2 will have to rely on another oracle scheme to get data from DApp1's front end, so which is not very efficient, not in real time. So what I have in mind is my current work is to design a blockchain native mechanism for data sharing to allow different DApps to share data directly with each other, so you don't have to go through another oracles for this task. So again, we can borrow some idea from PrivacyGuard, from Trust Extreme Environment, from TEE to enable this concept. So what I have so as you can see that I really want to realize all the stuff without relying on central authority. So decentralization is kind of my gospel. I believe in decentralization. I believe in you have to build in trust on the majority, not on central authority. So only by doing this, you can say trustworthiness is our main design objective. It's our main contribution. So with a final thought on trustworthiness, like I said, the term trustworthiness is controversial. So what I want to clarify, the first thing is decentralized doesn't mean trustless. So even if I say the system is decentralized, we still have to trust the majority of them is honest, like a Bitcoin, like a blockchain. And in our DecenTruth case, we are trusting the majority of the oracles are honest. And in our case of the Dept data exchange, we are trusting the majority of the Dept users are honest. So only by assuming that, you can get at least some quality assurance on your data. The second thing is using some kind of external or third-party techniques like TEE also doesn't mean trustless, because you are shifting trust from individuals to the chips, because the chips arguably is more difficult to tamper with. So you have trust instead of a trust on individual person or computer hosts. So that's my talk today. So any questions?
We have time for a few questions, so if you have questions,
Yes.
make sure your voice is big enough.
Could you go back to page 32? First of all, thanks for your wonderful presentation. It's very inspiring. Page 32, I believe.
32, yeah,
32.
32.
Oh.
You don't have 32.
Yeah, I don't have-
Okay.
Okay.
So yeah, here is also, yeah, this part is talking about how to have the user control their privacy, right? So my question is, for example, the data owner, you can, for example, configure how my data should be used or processed. And the information will be recorded in the smart contract.
Yes.
And if, like, I'm a user, I want my data only be processed or computed, and I don't want to use the service provider to store my data. I mean, in this way, I mean, which components in this graph will guarantee the service provider really respect what the user, like, configured about the policies in the smart contract.
So if I rephrase correctly, the question is, so what if the data owner only wants computation on my data, but that doesn't want.
This is just one example.
Yeah. So I think that's a correct direction in my opinion. So in our case, the data is not stored in the smart contracts. The data is stored in the off-chain cloud storage. So and everything stored and available to the data consumer is encrypted. Right. So what do you can only see the encrypted data, but only if you say you establish your trustworthy EE and you pass the attestation, and then you can procure the data key from the data owners. So yeah, so in this case, the data is never exposed. So the contract actually only encodes the policies, the usage policies, like say the data looks like this, looks like that. You can do average, you can do machine learning, or you don't know what the raw data looks like.
But how to guarantee like the data consumers respect fully of the policies in the data contract? For example, in the data contract, I configure policy 1, whatever it is. I mean policy 2. How can I know like the data consumer really like respect? I mean, data the correct operation on the policies.
Yeah. Yeah, that's a great question. So
Can you repeat the question?
yeah, the question is how do you enforce the data consumer? How do you force the data consumer to use the same specified policy or computation as was in the smart contract? Yeah, so basically that's why we do remote attestation. So because by doing remote attestation, the enclave is doing the measurements on what you have encoded in my enclave. So if the measurements measures the measurement report from which is already should be seen in the smart contract. So say basically you have obtained the same checksum on the program, and then you can be assured that the program running in the enclave is the same as it's supposed to be in the contract. So that's a whole purpose of why we use attestation to delegate the program from the on-chain space to the off-chain. Yeah, and also still by doing this, we are trusting the chip, the hardware, instead of trusting the consensus.
Any other questions? I have 2 comments.
Yes.
The references cited in this talk, can you send it to me so I can, so that anybody who is interested in reading those papers can, can have access.
Yeah, I'll do that.
All right. And the second question is, has this been used in real life?
So the first one has already been, so we haven't seen any adoption in our scheme. So I don't know. So the problem is, so we are assuming trust on the trusted external environment. So which is still a debate in the community. So even in Chainlink, they are white paper. They are using something similar to our scheme. It's called time-acquired TE-based scheme, but they are not adopting that. So the reason is the blockchain community, they are so reluctant to adopt trusted hardware-based solutions. But I believe as we improve the TE solutions, as time goes on, I believe we can. I do have the intention to pattern this kind of design in the future.
So you intend to, but yes, not been really. We haven't sent application yet.
We are in the process of designing a new scheme, so that the Dept data exchange is relevant to this project.
Well, if the paper is accepted, then within the first year, you are protected.
Yes.
Only within the first year. Any other questions?
Yeah, on Dept, on blockchain, even on cryptocurrency, ask me anything.
All right, we thank the speaker for the very exciting talk today. Thank you very, very much. How are you going to send the references to?
Yeah, can I send a list of reference to you as you can publish it?
Right. So that's my intention. Okay. Send those to me so anybody who interested in this